So I'm waiting. Okay, now YouTube. Okay, so we should. Okay, we're going live now. So on YouTube. Okay, so let me share with you what some of the questions and. So I'm waiting. Okay, now YouTube. Okay, that's fine. Okay, so we should. Okay, so these are some of the suggestions. If it's possible to show an example of those deposit on, so I'm assuming asking for a CT dose distribution. We have done this, and my question is to Dr. Hussam, why do you want to do this again? What is the reason? Because I don't think with EGS that is a good tool actually for doing some sort of plan analysis and so on. You can just get sort of a distribution, but I think that's the limitation of EGS. Remember, EGS is not a planning system. It's not a treatment planning system. It's an engine. It's a Monte Carlo calculation engine. Dr. Hiba, but basically the basic idea is you need to get CT images, and then you need to create a text file that has the names of all of these images, because we need to generate a phantom for those XYZ, a CT phantom. And that is how it's done. You need a text file with a list of all the files, DICOM files, and then we will use CT create. There is something about the CT numbers, and that's a bit tricky. But then basically the idea is that that program will convert the CT number into a material that you should have in your PEGS4 data file. And it can adjust the density of that material. So you could, for example, do have anything for air, for example, from -1000, let's say, to -700. You call any CT number that is within that range, you immediately assign the material to be air. And then from -700, let's say, to -300, then you can assign that material to be lung. And you can adjust the density of the lung, so you can make it a linearly increases within this range. And then from -300 up to certain thing, you can make it fat or tissue and so on. So that is the idea, or the basic idea behind generating a CT phantom using CT create. But we will not. I mean, still, my question is, why do you want to look into this again? Because if you want to think that this is a treatment planning system, it is not. Again,
Dr. Wamid, so we can put any source of radiation after creating these files. We can put like mapping of these files, and we can put any source of radiation to see those deposited around this source or not.
Yes, you can. You can. The source is something, and the phantom is something. So these are two different things. Okay.
Okay.
So with those XYZ, we were putting. You have two options. You can create the phantom based on CT images, and in order to do that, you need to first get the DICOM files, create a file that has the list of the DICOM files, and then you use the program called CT create. It will read the DICOM files, and then it will ask you, it needs to convert the CT numbers into materials. And that's the purpose of the CT.
That's good. That's good. After finishing the simulation, how to again construct an imaging to see the dose distribution after that?
Dose distribution, you have it. It actually has the program dose XYZ show. So using dose XYZ show, you will enter two files. It needs two input files. One is the phantom name, and one is the dose name. So usually they will have the same name, and then you get a dose distribution on it. Still, I don't recommend that, okay? Because with Dr. Hiba, the next comment was, on those exposures, can we try to source, try a source consisting of multiple phase space files, say tangential photon beams or photon electron mixum? Okay, I haven't done it. Again, these questions, to me, they are more like thinking of EGS as a planning system. EGS is not a planning system. It's a dose calculation engine. Okay. So for us, now, if I want to use two tangential fields, it's doable. It's not really trivial. It's not easy to do using EGS alone. But then the question would be, okay, are they equal weighted, different weighted? Where is the isocenter? And probably the critical question is, okay, do you want, for example, if you have a contour, you don't have contours with the EGS. Okay, so if you want a contour to analyze DVH, how are you going to do this with the EGS? You can't, because I don't think you can do. You have contours with EGS alone. Okay, so that's again, why do you want this? My feeling is you're looking into treatment planning, and those XYZ, EGS is not a treatment planning system. It's a dose calculation engine. Ismail, okay, doing a VMAT plan using MCTP, that is something. Okay, the question is, do you have MMCTP set or not? Okay, because there is a source. With Beam NRC, you can actually have a dynamic, or you can do that. It's possible. Configuration of MMCTP, this is probably we're going to do today. Okay, so is it possible to upload? And yes, we're doing this now. And Bilal installed MCTP in Ubuntu along. Okay, Zojo, and okay, he has problems actually. Well, he managed to install it, but then what to do next? That's the problem. Okay, before we start looking to MCTP, are there any other questions you feel I should address? I mean, if there is, just take the mic and go ahead. Okay. So I guess there are no questions. Okay.
Dr. Wamid, yeah,
Yes.
hi, good evening.
Yes, yes, yeah, go ahead.
I want to know that in your presentation, you have written that you have mounted the home directory in all the clients while setting up a cluster.
Yes.
So I have a little confusion when I tried it on my cluster. So I am surprised that on each client system, I am not able to see the local home directory. It is of the server system.
Yeah, this is what you want. That's the whole idea.
But
we want
the whole home directory is replaced with the server directory, server home directory.
Yes, yes, this is what we want. Why you don't want this?
But because I have 3 workstation T500 Dell Precision, so I want to do some parallel work like MATLAB and all those stuff along with the simulation. I want to use only just for the processing, not for the whole system. Like I do not want to block the whole.
No, but you're not going to block the whole thing. Still, you're just mounting a directory. I don't see what
after mounting the home directory of the server into the client, I am unable to locate the local home directory.
Yeah, but why do you want to locate the local home directory?
Because I have some data that I want to
just move it. Want to program it. Yeah, move it to the server. Just you move it to the server. Okay. So what you need to do is unmount. What you do is you unmount the home directory. Okay. And then, so now when you do that, the local home directory is going to appear to you. Move the files. use FTP or whatever, move it to the home directory in the server, and then mount again the home directory home server to all other your clients. The reason why you need this, you did not ask, why you need this. You need it because what happens with EGS, remember when you do parallel processing, it actually creates a log file. And that file, so that log file, all the computers need to access that log file to know, for example, how many particles remaining for simulation.
Okay.
And then also, remember, the results are also going to be located in one of these W files. So at the end of the simulation, it needs, then when this simulation finishes, it's going to combine these files into one file, not one data file. So it needs to have, so the best way is you share the home directory folder. So usually what I do is I make sure I have on the server, I have a big hard disk there. The clients, I don't care. I just, they can, I can have a very small drive just to have the operating system, because I'm going to mount or export the home directory from the server to all the clients. This is what I have, like in my Raspberry Pi cluster, because I'm still using SD cards, and the SD cards are 64 megs. I'm getting another Raspberry Pi, and I'm getting an external USB SSD drive. That is going to be like, I think 1 tera. And then I'm going to put it as the home directory in my server Raspberry Pi. And that will be exported to all other Raspberry Pis. So then I have really, also there is one recommendation that the SD cards are, they can be damaged easily. So it's better to actually, so this is what you need to do. You need to unmount it, move your files to the home directory in the server, and then mount again.
So that means it means if I want to do on one system like Python and another system like MATLAB,
it will work, because the MATLAB and the Python are actually executables on those computers. So you don't have to worry about this. It should work.
Okay. So is it possible, sir? Is it possible to mount only the EGS master folder to all the clients and then do the simulation?
Yeah, you can. So what you need to do, so that's another option if you want. So in the export, so instead of like /home, you put /home EGSnrc. Okay. And in the so you'll put /home /sing /EGSnrc, and then on the clients you will mount that party. Just make sure you have the folder created. So you need to just create the EGS home, keep it empty on the local home, right? Local home area, and then you mount that into that local home area. So it's possible. The reason why I do it this way, because usually when I was at university, so we have the system and people just access, each one has their local home area, and that's why I just export the whole home area to all machines. But if you only want, if you want to do it that way, that is fine. If no one else is using EGS, then that's fine. So it's possible. Okay.
Yeah. Okay. Thank you.
Welcome. Okay. So let me show you what I have, so that you just know the setup. So are there any questions, or are you interested to look into MMCTP?
We have one question to Romid. Please, sir, can you go over how to simulate CT, how to use EGSnrc for simulator?
I'm not going to go through it. We did it before. It's very straightforward. You just need the DICOM files. And then still the main question I have is, why are you interested to simulate on a CT? For me, that means you're interested as a treatment planning system. And EGS is not a treatment planning system.
Yes.
It's a dose calculation engine. I'm repeating this for the 5th time now. Okay. MMCTP is a planning system, and this is what I want to show you today. Okay. So let me just, before what I have. So now I'm accessing one, the main server. So this is the Pi, first one, and DF. Okay. So again, I have only. I'm still using the SD card. I still have about 60 gigs of data that. But what I'm doing is I'm exporting. So let me show you what I have. So this is the export file. So I'm exporting this folder /home to the network. This is like Samba sharing. It's Windows has something you can share folders, right? So you export from a directory, from a server, and then you will import on other systems. So saying what you need to do is you need to edit this. That is simple. Okay, Emacs. Okay, so this will be on the server. So instead of exporting the full home directory, then probably you will do something like this. Okay, and EGS home, and probably you will also need to export the hen house. So you need to export both. So you need this, for example, and you can copy or duplicate this line. Okay. And then you will also need to export the EGS, the one that has the, it depends on how you did their setup, but you need to export both.
Dr. Omid, okay. If I have both the directories inside a single directory, like
fine.
I have,
You just export one. That's
okay.
Fine. Okay.
Fine.
So this is what you need to do. You need to change this, and so I'm going to exit. I don't want to save this. Yes. Okay. And on the clients, also you need to change something. So we need to go to, so now I have actually an alias, so M2, it will take me there. So there we need to change the fstab file. Okay, so export, let me just put it as. I use Emacs as an editor, but you could use Nan or whatever. Okay, so this line here, this is, you're going to change it /home. You will put /home/sing/EGS. Okay, and here you will put exactly the same thing. Just make sure on the local folder you have a directory called EGS_home. Okay, you need to create that, and then it should work. Okay.
Okay.
What else? Okay. Okay, so I have Slurm also working fine. I've noticed, probably this is for Bilal Hussein, as when you reboot, you get like the status is down and you struggle with this. It's very simple. So you issue the command scontrol, okay, and then you will put update, okay, and then node name. So let me demonstrate it, okay? So I'm going to reboot. Sudo reboot. I'm going to reboot Pi2, the second one. Okay, so sinfo, let's check. Okay, so now it's back on. If I do sinfo, This, you see, it's down. It does not come as idle because it's reporting, oh, something happened. I did not execute or exit properly. And I struggled really a lot with this, and I was constantly trying to restart the service. And then I realized, actually, when I did some reading, so I can all as control. As control is something to control. I need sudo because I need to be super user to do this, and I want to update node name. I think that's what it's called, and there it is, Raspberry 01. That is the node name. Sorry, 02, and I want to update the state to make it idle. Okay, so when I do this and as info, now it is idle. So all what I need to do is just to change the state from down to idle. So you can issue this command. This probably for sync also you have a Slurm cluster. Then when you reboot, for example, a client or the server, you will always, for me, I'm always getting down, for whatever machine that I have to reboot. And that, so you just issue this command. And so sudo s-control update, we want to update the status, node name, we need to define what's the node name, and what I want to update, I want to update the state of it to equal to be idle. Okay. Okay, so before we do the MMCTP, one thing you have to make sure, so I'm going to assume you have an Ubuntu computer. It doesn't need to be a cluster, but at least it's one single computer where you can do multiple parallel processing. You need to be able to access it remotely through SSH. Okay, so usually that by default is available. You need to, of course, know what is the IP of the computer. I like to, because I like to use static IPs, so I know the computers where they are and located. I think you can do IP A. So this tells you if you issue that command on Raspberry or I think ifconfig. Now I know, for example, this is my computer. This is the IP address for the Ethernet. I don't have LAN available. These are Docker. I'm trying to also play with Dockers and so on. But the IP in my network for this computer is 11. Okay, that's important. And I'm going to assume, because I have Slurm, that is where I want to submit all my jobs. It's the server, but it doesn't, So I have Raspberry Pi 01 is 11, 2 is 12, 13, 3 is 3, and 14 is 1. But I don't need this for MMC. Okay. Another thing that we need to make sure it's installed is you need to have an FTP server running. I recommend FSTP, very secure FTP daemon. I strongly recommend that to be installed. And then you need to configure one of the lines. I think it's in the Slurm configuration. But if not, all what you need to do is you need sudo command, Emacs, and etc very secure FTP. So I think it's write enable. This line here, I think in 31, we need to uncomment that. So basically we want, because this is how we're going to transfer files with MMCTP to our calculation cluster or computer is through FTP. So, and communication is going to also be through SSH. So these two things, two services, you need to have them on the computer. You're going to send calculations there. Okay, so now I'm going to switch to my Mac, and so we'll stop sharing, and I will share a screen. I will share my desktop. Okay. So let me start from scratch. Before I start MMCTP configuration installation, any other questions? Okay.
What if actually we have both EGS and the MMCTP in the same machine?
You could. It doesn't matter.
Do we have to still configure that BSFTPD?
I think you will have to.
Okay.
Okay, but
Can we just direct the directory, that folder which contains EGS to this?
well, it's MMCTP, the configuration of it. You're going to see it now. You're going to see why you need it. Okay, okay, but you will probably need that. Okay, so I'm going to start scratch. I'm going to, okay, so applications and MMCTP. Okay, so I'm just going to basically, if you just need to follow the instructions of installation. For Mac, we download mmctp package, and we need to create an mmct directory. And we also need to download this configuration file, and we put it in that directory. Okay, that's how it's done in Mac. In Linux, I did not try to install it in Linux. I did not do that, and definitely not for Windows. But just follow the instructions. Now, if you're doing it with Mac, and with Catalina, if you have Catalina Mac 10.15, I think, you're going to have problem. This is not going to work. This executable, there are bugs in it for Catalina. And I have actually downloaded the source, modified some stuff, and now it works. But don't be surprised if you have if it does not work with temp. Just let me know if you have Catalina. I will give you the correct executable, and you can play with that. Okay, but it has problems. The version, Andrew, I sent him a few messages, and I'm trying to point out. I'm trying to help him to update it because I've managed to fix that problem. But I think for older versions of Mac, there is no problem. Now, we need to actually make. I like to put in the documents. This is I make a directory where I want to put anything related to MMCTP. But that is my preference. You can put it anywhere you want. You can put it in your home area, for example, or I don't know how it's done in Windows, but in Mac, I'm putting this in my documents folder. There is MMCTP. Okay. Let me also new folder, because I want to remove what I have from there. Okay. So I'm just going to temporarily remove everything or copy it here. Now, there are a few folders within the MMCTP that you could put everything in one single folder. There is nothing wrong in that. But I like to actually put separate folders. For example, the DICOM folder. This is where I get my DICOM files, and I will be putting them there. Because when I run MMCTP, I want to import DICOM files. Where are the DICOM files? By default, is going to assign this directory that, okay, read that, but you can read from other locations. We need another folder, for example, for EGS, for MMCTP to store, for example, the results of the calculation and so on. So this is called McGill RT. You can call it whatever you want. It doesn't matter the name. Okay. Beam NRC is configuration of Beam, but you can put everything in a single folder. VMC, that is Voxel Monte Carlo code. I think that's a commercial code. I don't have access to it, so you just need to don't forget. Commissioning is if you have any data. I still don't know why we need it, but if you have data for commissioning your Linux, you can put it there. So then it's a reference for you. CAD plan, this is an old planning system. If you have CAD plan format files, then you can put them there and so on. RTOG, this is for submission and so on. But essentially, you can put everything actually in one directory. And now you'll understand my point. So once I have MMCTP installed, then I will run it. So, okay, I don't want this because Oh yeah, because I need to clear the folders. So let's do it. Okay. Documents, mmctp. Okay. So I just want to delete. I want to delete those. Okay. And what else? The DICOM. Okay. I'm going to delete those. Okay, because I don't think I have anything else. So now when I launch mmctp, let's repeat it again. So we get this window. This is basically the list of patients that you have calculated with mmctp and so on. Definitely, we did not do anything, no calculations. So there is nothing. Okay. Then if I go to this file menu, the first thing I need to do is to go to the configuration. Okay. And definitely, I will need to go to the system admin settings. Okay. Don't worry about this now. This is the folder location preferences. You remember, this is why I was, I like to separate things. So I will create under mmctp, under that folder, I will create a subfolder called, we call it McGill RT or RT. You can call it whatever you want. This is basically the folder that plans, calculated plans will be stored there. Beam NRC input folder, so that's configuration for Beam DICOM folder, and so on. So I like to separate these folders, but you can actually, so here CAD plan, for example, it's, so you can change, think of the way you want to structure, where are the files kept and so on. Okay, so that's the first thing you will need to do. Okay, the next thing then, so we close. The next thing is we go to the configuration, and these are the shell. Okay, the shell is basically a node or a computer that you want to send calculations to. So for example, I have my Raspberry Pis, that is a shell. So I will need to define where is that cluster or computer that I want to send calculations to. You can have multiple. So if you, for example, could not succeed with Slurm to create one single cluster, that is still fine. You can have, if you have 3 computers, each computer you can configure it as a separate, node or calculation. So then one field will be calculated in one computer, the second field will be calculated in the next one, and so on. So that is fine. So once you open this, you need to the shell login. Okay. So because I have everything configured, I'm going to delete the shell. So when probably you do this for the first time, you don't have a shell. Okay. Remember, shell is where you want to send the calculations to. So I will make a new shell. Okay. Then I will give it a name. For me, Raspberry. Okay. Raspberry 01, because that's one. And the IP of my Raspberry Pi 8.11. That could be different, for your machine. Okay. Mac, Linux, or a PC, you can define. So mine is a Linux machine. Now the user, the way I have configured my Raspberry Pi, let me just show you under Home. Okay, so I have, the way I've done it is I have a Pi is, the default user for the Raspberry Pi. If you have Ubuntu, you will not have that, not a problem. This is my user name. I have a user, my name, Abdel. I have a user, I called it EGSnrc, and I have a user called mmctp. The reason why I like to do it this way is, for example, I want things done for calculation of treatment planning with mmctp, to be placed in one folder. And then I have my own stuff. I want to, for example, determine correction factor for a chamber or whatever. So the EGS, the beams or those XYZ and so on for my use is different than what will be needing for we will need for MMCTP. Now to save space, so instead of actually installing henhouse on each user, for example, now I installed EGS actually on one user. So there, that user has the henhouse. And then if I look at, so let me show you switch user. Okay, so who am I? Okay, so now I'm user Abdel. Okay, if you notice, I don't have actually henhouse directory. If I go inside there, my home directory, I don't have a henhouse. Why? Because I'm using henhouse from that user, EGSnrc. And this is in the bash. This is a bit, maybe it's a bit advanced to some of you, but so I'm using, so the home directory, I'm defining in my bash system, home directory to be wabder EGS home, but I'm getting the henhouse from this, whatever is there. The reason why I do it that way, suppose a new version for EGS comes out. What do I need to do? Then if I don't have this configuration, I need to then update the henhouse in my home directory, in the mmctp home directory, in all users, home directory. Each one needs to do that separately. But if all of them are using henhouse from one folder, I just need to update that. All what the users need to do, they need to recompile their user codes. That's it. That's what they need to do. Okay, so this is this is my preference. Okay, but you don't need to follow that. It's up to you. Now, so the user I have is mmctp. Okay, I'm dedicated user mmctp, and the password. For me, to make things simple, I use the same password. So my password is mmctp. Okay. Line feed prompt. This is for EGS, for mmctp to know, for example, when something has done. When it executes a shell command on the Raspberry Pi, things will happen and you get some text. And then at the end, it reads and see, okay, what I mean is this. This is the shell prompt here. Okay, so now for my user area, it is actually this tilde and then a $sign. But if I go to henhouse, then it becomes like this. mmctp, okay, cd. So with mmctp, that particular user, I have defined it that the shell prompt is always going to be at the end mmctp $sign. So when this text, when it's read by mmctp, it knows that, okay, something has finished, something has been done. And that is done through the bash. I think if you look at the documentation, so basically it's in the bash file mmctp is, I'm doing this, the export ps1 equals to something. That will make the prompt look like this. So user $, it's going to put mmctp always. So wherever I go, so even if I go to the home directory, you will always find mmctp $sign. This is needed so that mmctp then can know that, distinguish, so this is the recommendation. So this is the line field prompt. Whenever it detects, okay, this is there, it means, okay, I need to issue a command or do something. And the shell is bash. Connect test, connection test. So if I hit on that, it should test that.
Called the environment, Dr. Omid. Environment.
Yes.
Like environment, like an environment.
Yes.
Yes.
Okay. So that's for environment is for PCs. This is for Linux, I think. Okay. MCTP, that's fine. Okay, why this is? Oh, okay. Now I know why. Because this is 168. That's the reason. Okay. So now I should get an OK. Let's see if I can access it actually from outside. So 11, yeah, it should work. Okay, why it's not working? Raspberry Pi 01, 8.11. I don't know why it's not. I'm not getting an OK here. We should get an OK. Did I put the password correct?
Maybe the connection should be Mac, not Linux.
No, it is the Raspberry Pi is Linux, right?
Okay.
So
Yeah.
this is, I'm defining where I want to connect to. Okay.
You can use your old files.
Okay, but this is the point, you know, this is what, okay, let me continue. This, I should get an OK here, okay? Let's see, because I can actually see what's happening, the shell run. Okay, it says connection to host. Okay, it timed out, clear log. Let's kill all shells. Let's do it again. Okay, and shell run. I don't know why it's taking a long time or anyway. I'm gonna put my old files, but it should work. Okay, mmctp user is correct as mmctp. Yeah, it should be okay. I don't know why it's refusing. Let me, oh sorry, let me try it again. This, I'm going to use mmctp. Yeah, it's prompting me for the password, so this is fine. Okay. The next thing is, you know, you leave everything the same. If you're doing Linux, just leave everything the same. Okay. And here we need to check the FTP, the connection. Usually with Ubuntu and so on, we need the secured FTP. So I usually select this one, and when I hit on connection test, I should get an OK. Let me close. Okay, out of bounds. Okay. See, there are a few bugs in it, so it's not. Okay, let me try it again. Configuration, remote shell, and then shell login. Okay, so Raspberry Pi. Oh, I have this one. Okay, let's try again. Okay, you see now, I just need to reboot, to take an exit and come back. Probably it took some, you know, it kept the IP from old value. So now when I hit connection test, it gave me connection is okay. So this means SSH works, no problem. Here, usually with FTP, this doesn't fail. Okay, so if you use the secured one, because the very secured FTP daemon, it's SFTP. So now it works. So now I have the two things that, you know, I will need. SSH works and FTP works. I have no problem. The last thing is, you know, the queue. Okay, so if you don't have Slurm installed, you select, okay, it's going to be at, and that will be the number of cores. So here, the maximum running jobs. So this will probably you want to state, this is going to be, let's say, 10 cores. You know, it should match the number of cores that you have in that particular machine. For me, I have Slurm, so I'm going to select this. Okay, and I have one queue that I have defined, and it's called long. Okay, and there I have 16. But with Slurm, I'm going to actually put a large number. So I'm going to put 100. The reason why you don't do it with 80, when you submit a job, it will execute it. So if, for example, suppose we submit a field of split to 10. then it will be executed with 100%, it's occupying CPU 100%. Now, if you submit another 10 fields, a job with 10 split with 80, it's going to also be executed. So it's going to share the CPU with the previous 10. So each one, now you will have 20 jobs running, and each one will take 50% of your CPU. Now, if you submit a third field, then it's going to be also shared. It does not queue the simulations, but Slurm does queue it. So when I submit, for example, the first, suppose I submit 16, it will distribute the 16 to all the nodes that I have, calculation nodes. Now I submit another field with 16. Those will be submitted and will be temporarily placed in the queue. They will not run for calculations until one of these jobs that are running finishes. Then Slurm will start to submit. So that's why I can actually make the maximum to be, I can submit 100 or more, because I know Slurm is going to queue them. It's not going to overload the CPUs with jobs. This now, the last thing, this is very important. This is, we need to define where is our user code, okay, for EGS. So in my case, I have it under home and mmctp, okay, and it is EGS home. Remember, I have this user mmctp, particularly for this, and under it we have EGS installed under EGS home. That's all what I need to do for this shell. I can go, for example, suppose I want another shell. I can go and say, okay, add a new shell. Suppose I want to make another shell. I will just show you. Berry 02, okay. 12, Linux, okay, mmctp. And password, mmctp. Okay, so let's check the connection. Connection is okay on this one. Now this should work. I think, I might not, yeah, okay, I have it actually, FTP installed. Now, suppose I want for the second one, I want to put 80, I could do that. And here I put 4, okay. And here again, I will do home slash mmctp slash EGS. Okay. By the way, this could be a different cluster. The shell, it could be a cluster in Canada now, or a cluster in the doesn't need, these are just connection to cluster. It could be even a different, it could be a Mac cluster, a Mac calculation cluster for EGS, or a PC. It does not need, like in my case, it does not make sense that I access the cluster or calculations from 2 nodes on the same cluster. It does not, especially that I have Slurm, end of story. But in case you do not have Slurm installed, this is probably what you will need to do. You will need to define a shell per computer so that you can submit each job to a different computer and it runs there, okay? So we're going to leave it, no problem. So we have done that, okay? The last thing that we will need to do is beam models, okay? Now, I happen to have actually a beam defined, but if you don't have a beam defined, then you will, so let's make a new model, okay? So I will add, so let's put, for example, a Linux name, a different, okay, I have this, 15, and then we'll add this, okay? So now I don't know why I don't have only one. Okay. So this is basically a Linux name that when I read DICOM files, the DICOM files will have the Linux name. So I want the system, when it detects that Linux name, to assign it to a specific beam model that I have in my EGS. Okay, so the way we do this is we need to, okay, this is the Linux name. If you get DICOM, if we read a something with this name and this energy, okay, that is a variant machine, for example. We could select to be an Electra machine or Siemens or whatever. So initially, probably the best way to configure this is you read the DICOM file, and I will show you how. So you don't go through this point yet. You read the DICOM file. Then the DICOM file will read the Linux name, and it will automatically put the information here. Then you come back to the to this configuration, the beam models. You should find it, and now you start to see, okay, what's the MLC settings? These will automatically be populated for you. Okay, so the leaves, these are leaf pairs. They're not binary. Binaries for Tomo. Okay, and these are the bands, where the leaves are. If this is a Millennium MLC, it's not the high definition. So these are the positions of MLCs. Okay. Accessory settings. I don't configure this, but you could, for example, if you have a physical wedge, you can put a wedge and put the angles and so on. I really don't, because we don't, in our plans, we don't use physical wedges. Dynamic wedges, we have, you can actually put the STT file for the 6-degree, that's for a dynamic wedge. I don't have it for 10 or for 15. I have it for 6 and for 18. And those are for an old Clinac machine, and I think they are the same for the TrueBeam. But I'm not really worried because I don't use them. Now, the treatment, this is important. Okay, so remember the shells we created? Okay, now they will be populated here under that Linux. So for the Photon, TrueBeam, Rose, Energy 6, those are available shells. Now, where is the Linux model for this machine? So in my case, I know it's going to be, so that we need to define the beam NRC folder name. So I know it is beam, okay, TrueBeam, okay, and it's the same here, beam, TrueBeam. So whenever a calculation comes and the machine Linux is TrueBeam Rose with this energy, then it will go, and when it launches the simulation, it knows that the beam TrueBeam is actually the beam model that it needs to be used. Of course, that already exists in my under mmctp. So if I go here, the home, I already have the beam TrueBeam there, and that is, we have done this so many times. So it's in the spec modules. Okay, so I have this is the TrueBeam module. So there I can, if you want to do it with the GUI with Ubuntu, you can do it. Here I with the Raspbian, I have to do everything from the shell. So I don't have a problem with that. So it's the command beam build. Okay, and then I put the accelerator name. It will create the folder for me and so on. Okay. CD. So if I had, for example, an Electra machine, okay, then what I need to do is I will need to go here, let's say beam. I think I have an Electra machine. Which one is it? The Versa. Yeah, so let's talk the Versa, okay? So I can do this beam build, and then it's the Versa below mirror. Suppose I have that, and I don't need the support module. Okay, so now it created the Linux. Okay, now I should find a folder of my Linux, beam Versa below mirror. So if I have a plan with a Versa machine called, for example, something like that, then here in the shell, I will need to say, okay, the beam folder for that Linux is going to be beam Versa below mirror. Okay, so once this is created, we need to compile it. Don't forget when you do this. So we need to always compile it. So okay, so there I'm inside. I need to do make, and probably because I don't like to keep face files, I will compile it also as a Beam library. MMCTP supports Beam libraries, no problem. Okay, clear so far?
Dr. Vamin, if we have multiple machines, then is it possible to configure the multiple machine at the same time?
Yeah. So here, for example, okay, Beam Linux. So for example, I can change, okay, I can call this Versa, okay, and 6, so I'm going to add Versa, okay. Okay, so now I have, sorry, I need to, okay, probably now okay, to Beam rows, okay, that's the original one. So what I need to do is make a new Linux, okay. I'm going to call this, I can make a different energy, okay, but let's just, we make it Versa, and energy could be 6, 10, okay, and then, so I will need to, okay, it's a bit buggy, you know. Okay, now I did add. So now I have a Beam mode, Photon, Versa. So I have two Linux, the two Beam rows and the Versa. Okay, I can make another one. I can make this to be an Electron. So let's, okay. So let's go and select a new Linux, and then I'm going to make this Electron, and this could be also, you know, but because when the spec modules, well, it could be not a, this could be through Beam, again, rows, no problem, and this could be, you know, 9, and I will add this. Okay, so you need to just, you know, build up your inventor of Linux, okay, and define them to be here. For example, the Electa Versa HT. So this is an Electa machine, okay, and now the MLC settings are probably, then I need to define something for the Versa HT, okay. So this we need to make a new MLC and define something for the Versa HT. How many leaves? That's probably 160. So that will be 80 per bank. Okay, or 81 here, because we need to specify these are boundaries, accessories, and treatment head calculation here. Then for that machine, I'm going to put down, it's going to be the Beam Versa below mirror, for example. Okay, so let's delete this. This is our true Beam. This is very important, okay? We need to have an example of an input file that is going to be used with this machine. So what I've done is I have an input file that I was doing for commissioning or, you know, playing around and so on. And that file should, I'm going to put it, I will put it under the Beam folder. So this is the file. So if you have done something, input, and it's an example of an input file, okay? In my case, for the TrueBeam, I'm using a phase space as a source. So that's why, but if you're using a target and so on, then you take that input file and you make sure that the Linux model is, you know, has all of these component modules. But for the TrueBeam, I think I have 3 component modules only, because I'm using the phase space file above the JAWS as an input for the rest. So this is an example of an input file that I use, created with EGS, with Beam. This is a file that I've created with Beam. And if I open it, okay. So this is a typical file of a Beam input file. This file, if I take it and execute it on the Linux Beam 2Beam, it's going to work. Because in this file, this is where the source I have defined. It's a phase-based file, and I know where it is going to be located. And why is this important? Because everything is, I mean, above the JAWS, even if you have a full file, being modeled with target, flattening filter, and so on, everything remains the same for that machine. When the MMCTP wants to submit, for example, a new calculation for a different field, it's going to automatically modify your JAWS settings. So I think this is JAWS settings is for a 10 by 10, if I'm not mistaken, or maybe something asymmetric because I see zeros here. It will modify, it reads this, it's going to modify them and put the correct field size. Again, for the MLCs, okay, the MLCs, you see it has some settings. This is, I was trying to do some troubleshooting. It will replace the MLC positions with whatever MLC configuration you have from the plan for the beam. If you have dynamic MLCs, it's going to actually, because it's not, this configuration is for a static. In the MLCs, then it goes and reads the MLC dynamic settings from a file. It will create that file and modify this so that it points to the correct file. I'm going to show you all of that. Also, if you have dynamic JAWS that move, then this is static JAWS. Then it will actually make a file that has a dynamic, and that file is readable by EGS. Okay, that's the because if you export the MLCs, for example, from let's say from Eclipse, that format is not readable. It's not ready for EGS. You need to somehow convert it. You need to build, and mmctp will do that. It does have that. Okay, so this is now. Let's go back to
يعني if is an example to convert it using this.
Yeah, I'm going to show you.
Okay.
I will show you how because it reads a DICOM file. It reads. So let's move forward. Okay, this is something I'm struggling really now to define an output of, because Monte Carlo, remember, it just gives you a dose per incident particle. Okay. How can we translate that into an MU? Because in a plan, we get 100 monitor units, 200 monitor units. How that's translated. So there is a calibration for that. So basically, you need to run, let's say, a 10 by 10 field and record the dose at Dmax. So the dose at Dmax is going to be, I'm going to show you all of these things. Is going to be something, okay? Then you come here and say, oh, okay, that value is 1 gray, equivalent to 1 gray. But I'm struggling a little bit with this part. Okay, so now close. The next step is, okay, so now essentially I have everything ready. So I have the shell configured, the beam configured. Yes, so this is, let me just go back to the beam. Okay. File, import, configuration beam model. Okay. Okay. So here I have to point out where is that template for my input file. So I've placed it actually in the Beam NRC folder. Then I will go and select it, and that's it. Now, what's the PEGS file name? I know for my Linux, it's called Linux. I called it that. But if you have used a different name, then you need to specify what is the PEGS file name. So this is now, it's ready. It's ready for, we can submit things. Okay. We can go now to open patient to get rid of this. Okay. See, it's a bit buggy, the code, and I'm trying to help Andrew. I mean, it's a great job, but you know, usually there are always bugs. Okay. Okay. So the next step is, okay, this is my patient folder. It's empty. What I need to do now is I'm going to go to my DICOM folder, and I'm going to put back the DICOM files. Remember, I removed them. So let's put it back. It's in the documents. Sorry, it's in the desktop. And is it here? This is it's a different folder. Okay. So let's take. So in Eclipse, I exported DICOM with DICOM RT and with the structures. EGS alone you cannot have structures there. So those XYZ view, you don't have structures. You cannot, if you don't have structures, you cannot actually generate DBHs. So I put them back in the DICOM folder. So we close this and go back to the file, and now let's import. So I'm going to import an RT patient. See, if it's there, it's going to read the DICOM files in that folder. Okay, and then this is the patient I have, and I just select and transfer. So now it's reading the DICOM files and converting those files into a format that is used by mmctp and also could be used essentially for those calculations. Just have to wait a little bit. And now it's bringing the structures. See, I have body, I have ring, I have PTV. These are structures. And now it's getting the dose distribution because I also exported the dose distributions from Eclipse. It's also going to read the plans. And of course, because the Linux that I've used to generate the plans for this patient is TrueBeam rows. So it knows that it has a plan, a Linux defined called TrueBeam rows. If not, it will give you a warning message that, okay, I don't have a Linux with that name. So for example, we have a TrueBeam Ocean machine, but it's not configured. And then when I import a patient, a plan that TrueBeam Ocean, it's going to complain, say, okay, I don't have a Linux called TrueBeam Ocean, but it will put it, with listed. So I need to go back to the Beam NRC configuration. And then all what I need to do is just define what is the location of the beam model for that Linux. And it happened that, you know, I'm going to use exactly the same one for the ocean octopus. So now, if you have EGS and MCTP in the same machine, you see, because we have to define the shells, so I think you will probably still need to communicate. So it's going to be an SSH to a local machine, an FTP to a local machine. It's not like defining directories. So you will probably need, now, yes, so I think you will need to just, I think, have the SSH. If you don't want communication from outside, just unplug the Ethernet cable from a machine. Okay. But probably you will need that because probably you're going to transfer files. So now it is there. Okay, why I hit on this? Okay, close. I hit on the wrong button and it's reading the icon files again. Okay. So now remember the list, the first thing. Okay, I have the patient there. I have imported the patient. Now, okay. I can select, this is the CT for that patient. And now it's going to open, because now it created a McGill patient, sorry, plan. I mean patient. So remember, this McGill RT was blank, was empty. Now there is a folder. Under that folder, it has the CT, for example. It has we have 8 plans for this patient, okay, and so on. And this is one of the bugs I don't like in this system. I'm going to show you now. So for some reason, it does not know which dose distribution. So Eclipse, I exported also the dose distribution for the different plans. It does not know which dose distribution belongs to which plan. So what happens? It's going to just list for each plan, 7 or 8 dose distributions. You're going to see this now. Okay. So this is the Phantom CT. Okay. Structures. That's the big advantage. We have structures there. I can, in the view, for example, panel, I can select which structures I want to be visible or not. Okay. So that is something you can do from the view panel. Because I have a linear defined through beam rows, you're going to, I mean, it automatically detect, the machine and energy. But if you did not make a linear, then this would be blank, and then you will need to go and define, configure that machine. What it has done now, it gave me this message. From this CT, it has actually created a dose XYZ phantom. So here, it has created what's called this thing. I'm going to show you later, because this is a CT numbers. For Eclipse, for EGS, we need to define medium. It's voxels. We need to define, okay, this is air, this is water, this is bone, and so on. How does it do it? It's I did not talk about it because this probably I will make it later. This CT models, it's basically a ramp. It uses what's called a water ramp. Basically, this is what a typical planning system does. All the voxels are water, actually, okay, in a planning system, even with heterogeneous correction. All what it does is then changes the density of each voxel, but essentially the dose or material assumed to be water. So here we're defining, this is a model number, water, for example, from the CT number from -1000 up to 0, use the density to be 0.001. Essentially, this is for air. So it's air, all right, but the material in the planning, and it's a water ramp, air, and then the density at 0 is going to be 1. Okay, then from 0, CT number 0 up to 6000, change the density, how it looks like, and so on. This is something, essentially, that's the advantage of Monte Carlo. We are going to create then later on our model for CT numbers. So we can put, for example, from -1000 up to 700, I'm going to use a material different. It's going to be air, for example, and define the densities. Then from here to here, and I hope with Bilal, we have actually commissioned a GE machine, and he has done work on the Cyrus Phantom. We can bring those results and try to make a proper, actually, model. Because that's the advantage of Monte Carlo, is heterogeneity corrections. Okay, three-plan system, yes, these are approximations, but Monte Carlo gives you better, results there. So, okay, so once you have, this is the problem. It has actually the those. So I have here how many plans? 8 plans. So 8 plans will be listed for each. 8 dose distribution will be listed for each plan. Now, which one is which? The easiest way, I will go to view and I'll put color wash. Okay. This one, I know this plan is a calibration plan. It's basically a simple 10 by 10 coming from above here. Okay, definitely this is not the distribution of it. So I'm going to select that and I'm going to delete it. This one is definitely, it's not the distribution that for that particular, okay. This is a parallel opposed field plan. Okay, I think the next one, yes, this distribution belongs to that plan. So I'm going to keep it, and then this is for a head and neck. I don't need that. Okay. So this plan, I call it calibration. It's basically a 10 by 10 field on a phantom. And that's the distribution from Eclipse. Okay. The next step we need to do is, okay, we go with beam. So I have the plan. That plan has only one field. Remember, only one field. And then I will double click. It will open for me this window. That's for submission of calculations. Okay, we can go to the advanced beam NRC, for example. So it's like a GUI. It's like a GUI that we used to see for in beam beam application. There we specify medium, I watch. Remember all of these, you know, first time, phase space file, number of histories, you know, and what's the source number. Okay, now because I'm using a phase space file as a source. Okay, I don't know why it brings photos. It should bring everything. These are the 3 component modules that I actually have in my library. And those ones are the variable ones. Those are, you know, so I have the dynamic variant MLC, okay, dynamic jaw, okay. Of course, now this plan, particular plan, everything is static. You could also hit on the edit EGS, and you can change a bit of the physics. So make sure that you have exact Presta to remember all of that stuff. Okay. So I close this, then I come back to here. So essentially what it's going to do is going to make a test run with 1500 particles. So when I hit run, it's going to submit everything to Raspberry Pi 1, okay? And if you look at the log file, we should start to see, you know, this. It's basically making sure that everything is fine. I can actually, so what it did actually is it used an FTP. It created an input file, used FTP to upload the file to the correct directory, and then using SSH, it entered to Raspberry Pi 1 and executed the EX, you know, beam and so on to execute this. And once that execution done, then it will report back. It read some values from here. So it's telling us, look, if you want a density of 500 particles per centimeter squared, you probably need this number of histories. And this is going to take, so I have 16 cores, for example. This is going to take about 2.2 hours. Okay, we could change this, you know, I could, look, I don't want that. I'm happy with, you know, just 100,000 histories. So, you know, that's going to take, you know, 1 minute, 1,000. What I do, I don't actually, so I run this simulation just so that the input file is uploaded there in the beam directory. Then, okay, then I will go immediately to the dose, okay, and then double click here. And now this is basically, I'm going to do a dose XYZ calculation. And in the advanced options, I select, look, I want to actually do a treatment head simulation. I don't want a phase space file. If you like a phase space file, you can go to the beam, create a phase space file, you run it, you know, and get some good numbers, and then use that as an input file, because here it's a drop down, if I can select that. But no, I like to do simulation for multiple directions, so that is fine. This, I'm going to put everything outside, it's going to be air. And basically, yeah, this is, okay, I can change a little bit the physics. I need to probably change the template. This is on, and you know, this, for bigger voltage, it's not really important, but this is something I like to do. Okay, that's my preference. Then we're going to close this, and we're going to make also a test run of 2,000 histories using the library, a beam as a library. So when we run, you can see here it's actually created. This here tells you what's happened, and now it's uploading it to that machine, and then it's executing it. Okay, so I can look at this log, and I'm going to see. Okay, now 1, 2, 3, 4. Okay, so this is 2,000 histories. Okay, and then it's going to report back some based on this. Okay, if I need, for example, to get the dose uncertainty down to 1%, probably I will need to simulate number of histories, about 4,000 histories. Okay, and that on a number of jobs 4, that is going to take 1.53. So now I can change this to 16 because I have 16 cores. Okay, then this is going to take about 20 to 25 minutes. Okay, I can also, just so that I make things quick. Okay, let's do, this is 33 seconds. Let's do, okay, let's do 5 minutes. Okay, so when this will take about 5 to 6 minutes. So there I can close. Then we need to submit now so that it simulates. And submission, we don't have a submit button, but we click on this. Okay. So now you see it knows that this is a request to do a calculation. Is going to upload, and let's terminal. Okay, here. So you see now the Slayer queue is getting filled with, okay, now it's getting filled with the jobs. Okay, so I have 4 running on Raspberry 1, 4 on 2, on 3, and 4. So now it's going to be running, and CD, and let's look at the log file. You see, this is the file. When you do parallel processing, it's a file that keeps you know, tells the jobs that, okay, there are still 940 million particles. So if I do it again, now it's reduced. So each one of these 16 jobs is going to take a few of those particles and run the simulation and so on, trying to reduce the number. Also here, this is going to monitor the progress. The frequency of, so basically it's sending SSH to that machine, and it's reading this log file and give you an estimation. The frequency of this is actually, this is, I did not, in the configuration, in the remote shell connection, sorry, not here, in configuration, in the system admin settings, the first page here, this tells you, okay, how frequent do you want the system to check the status? So I've reduced it. By default, you probably will have 1. So that means every 1 minute is going to check what's the status of the job. I've reduced it to, I'm impatient, so I've reduced it to 0.15 of a minute. That's what, that's about 15 seconds, 10 seconds. Yeah, I don't know how many seconds. Okay, there. And this is for submission. So remember when I clicked on the button, you saw like I got the job got submitted, you know, quite quickly. By default, this is going to be 1 minute. 1. That means when you hit on that check button, it's probably going, you know, it waits for approximately a minute before it checks, okay, anything needs to be submitted for qualification and so on. So if you're impatient like me, come to this configuration and just reduce those values. Okay, so I put them here. 0.1. I think this is 6 seconds, right? And this is probably 10 seconds. Okay. So it's going, it's running the simulation. Let's do something, because one asked me about. So here, I think for the mmctp, let's look at this head and neck. Okay. So for this head and neck plan, let's first remove, the distributions that are irrelevant. This is okay. This is the head and neck plan. Okay. And this is remove. Probably will not have a lot of plans for a single patient, but I had this for our phantom. So here, these are the beams. I have 9 fields. Okay, if I click on one, I get the beam properties. There shows me, okay, it's a dynamic. And this is the interesting part that I wanted to show you is here. So if I look at, this is how actually the leaves, it's a dynamic treatment for the leaves. Okay. I think you could import the MLC file. Let's try that. So let's go on the documents. Sorry, on the desktop. Okay. You don't need to specify something. Okay, it's not importing the file. It's not importing the file. Okay, that's probably a bug. So I need to look into this. But these are the positions of the leaf. Okay, and I think it depends on the position. So for each one, probably this configuration is going to be different. But when we submit, let me show you. So when we do this, okay, let's go to the beam and let's take this and let's run, a test. It is going to create for us 2 files, and I'm going to show you these 2 files. Okay, the first file is for the dynamic jaw. Where is it? Okay, and the second one is for the dynamic MLC. Okay, the file name, I want to show you the name. This is for the phantom. Okay, so it actually, so here, this is MLC sequence file read. It created a sequence file. So mmctp read the MLC file from DICOM. It generated an MLC file that is readable by EGS. That file is going to be here. So it's going to be in the beam folder. Okay, these are the jobs. Okay, XRun. I have a lot of stuff here. I was running. Okay, so this is for plan 8. So let's look at CD QA plan 8, and I have only one field. See, there are 2 files here. One is called the DJAWS, and one is called the MLC. Okay, so if we look at what's more under DJAWS, okay, this is a file that specifies the jaw positions, dynamic jaw, as a function of dose index. It's already in a readable format that EGS can read. Okay. The same thing is for the MLC file. Okay, that is also a file readable by MLC by EGS. these, I mean, look at the values. It's -2 and 3 and so on, because MCTP will convert, because what you need actually are the positions of the MLCs at the MLC level, not at the patient level. But in the DICOM file, you get the leaf openings, you know, at 100 SSD. So MCTP will convert everything back to dimensions that are relevant to the MLC plane, and generate the appropriate file format. You can Eclipse doesn't do this. Eclipse does something else. Okay, so you can, if you want to, I mean, if you're not using MMCTP and you want to do that, then you need to study the formats of MLC from Eclipse and what is required by EGSnrc, or by Beam in this case. And then you need to make an algorithm that knows where the MLC and does the magnification factors and so on, and then writes a file in this format. Okay, so let's go back to here. Okay, let's see if this has those XYZ. So let's see if this has finished. So SQ. Okay, so I don't find anything in my queue. So now the next time is going to check. We're going to get this to be 100. I would love to actually have buttons, go and check, go and submit, instead of submitting it into a queue and wait for appropriate time for it to, you know. Okay. Because I should get a message that, okay, I'm checking, and because I know this is at 100, finished.
Excuse me, Dr. Wamid,
Yes.
because I'm a baby in this direction. So for me, this radiotherapeutic, يعني radiotherapeutic DICOM
Yes.
image.
Yes.
Okay. For prostata or for what?
This is okay. You mean okay? This is actually it's a phantom.
Yes.
We have used this is not a patient. Okay, it's not a CT image for a patient.
Okay.
It's a phantom that we have used to commission IMRT and VMAT. So basically, it's from the task group 119. There they tell you, okay, go and scan your phantom with a given shape, dimensions, and then we will import structures. They have drawn these structures for us. Okay, and then they ask us, okay, this is a structure for a prostate. Try to do a plan so that this prostate, the structure in that phantom, gets this dose, and so on. This is not a patient, but it's you know, because I don't want to show patient images, but I'm just, so the best example is to show you, you know, a phantom.
Okay. Okay.
Okay, so I will show.
If
Yeah.
there is another mission, if you can create a treatment planning using this program.
Okay, that was one of the questions about, can you do a VMAT plan using this? VMAT is inverse planning. You see, there are things that people are confusing. IMRT and VMAT, those are inverse planning algorithms, right? EGS is not that. EGS is something you tell it, okay, these are the particles, go and calculate for me the dose. It's not an optimization algorithm. So what we can do is, in this case, I have the plan, I have the MLCs, I can recalculate everything in the phantom using Monte Carlo.
Okay.
But I cannot, especially inverse planning, I cannot do inverse planning with mmctp. I can do forward planning, that is doable, but not inverse planning.
Okay.
Because inverse planning, you need a different algorithm. You see now, I've just, okay, rebooted it, or so it went and checked, okay, I've done the calculation. I'm going to now import the results, and there it is. You see, we had one plan. I'm going to rename this. So I'm going to call this Eclipse, okay, and that's the, okay. And here, this is the dose distribution from Monte Carlo, okay. So this is essentially the dose distribution using Monte Carlo, okay. I'm expecting it, it should be the same, right? So it is the same, okay. Now, we can repeat, we can do the same thing with the VMAT plan, or with whatever plan that I want. But essentially, I'm getting a dose distribution. The thing that I'm struggling with is, okay, I want to actually, because now everything is reported. This is the plan from Monte Carlo is reported as per incident fluence. I need to change that. So what I trying to do, I'm looking at a dose profile. So let's go and look at for the Eclipse plan, and I'm going to ask it to give me a profile. So this is base 7.5. I could use the ruler, by the way. So in case you're wondering, I could use a ruler and drag these 2 points. So I want to profile from there, to here. But I like to just enter everything manually. So the phantom dimension is 15 centimeters. Large center is at the middle. So this point is going to be x0, z is 0, and the y is going to be 7.5. And I want from 0 up to minus 7.5 and 0. Okay, that is basically, I want the profile, dose profile along that line, and calculate. So here is the dose profile. I can show it on the Z. Okay, I can change the color. Let's change it to, okay. So now this is the color. This is a PDD curve, right? And the maximum, because I know I've used, in the planning system, I used 100 monitor units. So I'm getting 1 gray at Dmax, or the maximum dose Dmax. Now, let's do the same thing, but now I'm going to select the Monte Carlo plan, and I'm going to keep this the same. So I'm going to calculate. Now, this for the Monte Carlo plan, and I'm going to show again. You see, this is a bit noisy. It's Monte Carlo, it's obvious, right? But I need to then modify. I need to make this calibration that, okay, that particular amount of dose per particle, that is equivalent to 100 centigrade, for example. And this is what I'm struggling with now. But I could, so if I select both of them, okay, obviously they look bad because one is, has a, but I can renormalize. So I can normalize 2.7739 e to the power minus 13. And this one essentially, okay, that's fine. So these are the two curves. Yeah. This is one way to actually see if the beam model is okay or not. Treatment planning system. So let's make another profile. This is the Monte Carlo PDD, and that is the Eclipse PDD. Okay, it's not the measurements.
I'm surprised because you use the same data for Monte Carlo, the same input data given to the Monte Carlo. The true?
Yeah, but same. Okay, the planning system, we have measured data. We put in the planning system, and it has an algorithm. It produces PDDs. Okay.
Okay.
Now with Monte Carlo, I have an input file. I have a beam model, and with that beam model, I try to generate to see if my beam model can actually reproduce the measured data of the LINAC. Remember, this is something we talked about before we do the optimization. We use, for example, if I'm using an energy, incident energy on the target, I'm going to use 6, for example, MeV, tweak it to 6.2, put it 5.8,
Oh,
and
yes.
do a comparison of the PDD measured with Monte Carlo. Okay, so that is so. This is just to show you that okay, I do have a good agreement between the Monte Carlo model and you know whatever Eclipse. I'm assuming, of course, this is an algorithm from Eclipse. It's not really the measured data, but this it's a good representation of the measured data. Of course, we have some issues here in the build-up region. That's irrelevant for us. Okay, but let's look at the profiles. So since I'm here, let's look at the profile. So let's do another one. So I'm going to take a profile at D max. So let's see if that is good or not. So I'm going to, so X will be from minus 30, minus 15. Y, this will be at 6.0. Okay. And Z will be 0. And this will be from 15, and this will also be 6.0. Okay, and 0. Okay, I did it the other way around. So yeah, so we'll put minus 6. Okay, because I immediately saw it that the line was actually at the bottom. Now it's there at the top. See, it's there. So I'm gonna again select this. Okay, we're gonna calculate, and then I'm gonna select the other one and calculate. So I want to calculate the eclipse and the plan. These two, and again, of course, they are going to be quite. Where is it? Quite off. Okay, we need to normalize. I need to normalize them. There is, I just don't know why. So this we put. Let's normalize them to, let's say, put them to the maximum value. This is 1.
Because maybe the scale is changed.
Yeah, because I want to just make the scales the same.
Yes.
0.4047 E minus 13. Okay. And yes, okay. So that is the calculation. And this is Monte Carlo. It's noisy. Okay. And I'm normalizing to the maximum value, not to the value at the center. But imagine if we can actually, we do, I mean, this was for 5 minutes running. But imagine if we did this, I did it so that the uncertainty is actually lower. So I made it run for 2 hours. Then I would get a better agreement between the profile of Monte Carlo and the planning system. Okay. So what I'm struggling now with is to convert the MUs. This is because I want really with Monte Carlo to give me, I don't want it here to get this dose. I need to get, 100 centigrades or one gray here. It's like the eclipse. Eclipse, if I go to that point, I'm getting roughly around, where is it? Those is, yeah, it's just from the maximum dose, this is the maximum dose, and for Monte Carlo, see, it's a different scale. So this is what I need to change, and that is done from here. This is the calibration dose. I'm struggling with this. I try to put the numbers, and then things don't make sense. Okay. So I'm working on that, so that at least then I get agreement. So what I do is I do this for let's say for this plan. Let me show you what I've done. Okay, since if you give me just another 10 minutes, and then we'll be done for today. So on the desktop, okay, here, let me bring the folder that I have done. So that one deleted, and particle. Okay, let's open again. Okay, so now I have these two patients. That's the plan.
Can also working with different modalities like gamma knife and tomotherapy, like that.
It does have. I haven't done it. Okay, I have not, but it does have that. When the Linux that I see there, gamma knife, I'm not sure. It has cyber knife.
Okay.
It has Electa. It has Tomo, and the list. The list of things are actually on the Beam here configuration.
Okay.
Beam models. So we have Electa, Variant Electa, CyberKnife, Siemens, tomotherapy, other. Okay?
Other, you can define it, I think.
You can, okay, as long as you make sure. But then the question is, how does it then change the input files? That I'm not sure about it. I really don't know. But those, I work with Varim and it works fine. So this is what I'm struggling with, just to show you. Okay, that's the file calibration. That's from Eclipse.
The max
Then, okay, this is the simulation. I did it. It's okay. It was a dirty simulation. Anyway, just a small one. This is the one that I've done with a very long. I think this was 8 hours, because I went really for 0.5% uncertainty. Okay, so I took that value and okay, this is water. Basically, I'm struggling. My struggle is, let's do the dose profile. Let me show you. 0, 7.5, and then 0. 0 minus 7.5 and 0. So I'm going to take this, okay, show ruler. No, okay, I need this is this one was done, with a very low uncertainty. Okay, what I'm struggling with is this curve I obtained with an 8-hour simulation. I kept everything the same. Then I repeated the simulation, but instead of using 8 hours, I was using a less uncertainty, and I'm getting a different curve. I was expecting these two curves to match, but one will be noisier than the other. I'm struggling with this. I don't know what's happening. Did I screw up something in the input files? I'm investigating this, but essentially I want, because these two curves should be the same. One should be, so if you run simulations, let's say for 1 million versus 10 million, you should get the same curves, but one will be noisier than the other, because everything is reported as dose per incident particle. So if you do simulation 10 million, the dose is going to be larger, but per incident particle, you're going to divide by more particles. So you should get the same dose. That's how Monte Carlo, the EGS works. Okay, so I'm struggling with this part. What I've done also is, this is the bands. Okay, this is, for example, the simulation from the anterior field. Just so that I show you what is this. This is a step and shoot plan, actually. So you get steps right there. Okay, so the MLC geometry is actually something from Eclipse, and this is the simulation from the anterior. This is simulation from the posterior, and I think this is the combined. Okay, and this is from Eclipse. This is how the dose distribution looks like from Eclipse. The problem I face is that the doses are not the same. Okay, see, this is 4 point something. If I take a profile, you'll find one is higher than the other. So that's a calibration problem. If I normalize, I get the same thing. If I normalize the data, so if I go and do those profiles, let's delete those. Okay, and then we will use the same. So let's put the profile in the center. So this will be 15. This is 0. And then this is minus 15, 0 and 0. This is the bands, this is the Monte Carlo. Okay, and this one is from Eclipse. And when I do that, okay, this is what I don't like. These two curves, if the calibration is correct, they should match, but they don't. Okay, if I normalize, I get them matching. Okay, so if this is select this 3.865, okay, that should be enough. And here this will be 3.2165. Okay. Okay, you see they match, but not in terms of absolute dose. And that's a calibration problem. An MU, what's the definition of an MU in terms of Monte Carlo? That is a problem I'm facing now. Okay. So I hope you enjoyed using this, and just to tell you, why this is, we can have DVHs. That's something we lack actually with the EGS code. So here, I can show you. There are a lot of structures because that's when I was doing the optimization. I forgot to actually remove them when I was importing the files or exporting them. But okay, just bear with me a second. Okay. There is a multi-target. So these three targets, these are 3 cylinders. You can see them. So if I remove, okay, these are 3 cylinders. For example, it's one of the plans that we need to do for TG51. And then you can actually calculate the DVH. So for example, for the center cylinder, for example, I can select center and then show. Okay, could not read the DVH. Why? Okay, I did not do it, but I know it's something we can do for center not ready for DVH calculation, creating structure points. Okay, now it's doing this. Inferior not ready for creating structure points. Okay, and then how do we show the DVHs? Oh yeah, here it is. Okay, but that's Hansfield unit. Okay, I don't want that. This is the Hansfield units. Okay, here we have something that looks volume and dose. No, but those enhance. This is okay. That's not a DVH. I think we should get a DVH somewhere here, but I don't know why it's not showing. So anyway, these are the the stuff that I'm looking into with the MCTP. Definitely, there are bugs in it, and we're fixing it, trying to improve on things. But it has a very nice way of sending stuff to the EGS, communicating with EGS calculation, and so on. So I hope for those who are interested in configuring or running mmctp, that maybe this lecture is an introduction to how you should get started.
Thank you, Dr. Omid.
Yeah, there are bugs.
For viewer,
Report, yeah.
excuse me, for RT DICOM, if there are extra viewer for it other than this program يعني في برنامج تاني يقدر يفتح
I'm not, maybe Bilal knows about this.
Yeah, there is a Plan UNC. It's
okay.
treatment planning system from University of.
I have it.
Yes, you can use the Plan UNC and interface with the EGSnrc, and you can display also the those through this.
Okay, thanks.
So that planning, it can interface with EGS, right?
Yeah, it can do.
Okay, yeah. Okay. So it's a different, you know, this one was a PhD work by one of my colleagues, Andrew. And, you know, he did, I think, a decent job. And there are a few people who are actually working with this, because I see people are reporting bugs. And please, if you become a user and there are bugs, you know, or things you request that you wish that, you know, to do, you know, just go to the Git page and just put it there, because that's how developers will know that there are bugs and so on. If you're doing Catalina, if you're doing with Mac with Catalina, I already know it's not going to work. So that I have actually fixed this bug for Catalina, and it's working now on my computer. But if you're using an older version, you should not have a problem. I haven't done it with Linux, but try if you want to put it on your Linux machine, do it. Nothing should prevent you from doing that, and you should report the bugs, and we will fix, you know, the Linux version. Not a problem. Okay. So I hope today was. Yeah, you have.
What is the use of the VSFTPD in the cluster formation?
How to configure it, or what do you?
No, not in the not mmctp. I'm asking generally in your presentation you put that we have to install the VSFTPD.
Because this is how you put the files.
Is it only for the mmctp, not for general cluster formation also we need?
Well, because usually I for example, I have I do, for example, I have Ubuntu on my laptop, okay, virtual machine. On it, I actually develop, for example, what's the input files and so on and so on. But on my laptop, I'm not going to run a simulation for 9 hours. So I need to transfer whatever files I have on my Ubuntu machine, virtual machine, to, let's say, to the cluster. How you're going to do that? The easiest way is you use FTP to upload files, or you could use secured copy. You can do that, whatever method. But the easiest, because a lot of us have actually FTP clients, so you need to just activate FTP server on your cluster. But it's not essential. It's not. You can. I mean, it's only a way for transferring files. Even
one of the ways for that. One of the
yeah.
ways.
Okay, but definitely, if you're using mmctp, because you can copy files using secure copy, SC copy. That will do it through.
I installed mmctp in the same Ubuntu machine.
Yes.
Which is running EGS.
Yes. So try, see if it's fine. If it's not fine, if it doesn't work, this could be the problem. Okay, the problem and the problem is that it's by default mmctp is expecting to transfer files through FTP port 21. So if it's not working, if it, you know, that might be the problem. So all what you need to do is just install on Ubuntu or another FTP server, FTP client.
Okay, separate client. Yes.
Yeah. VSFTP server, you know, I like that, and you just need to open something. You know, you just need to modify the something in the configuration file. But mmctp, I believe it probably requires that.
Thank you.
Because the way it's written. Okay. So how did you find overall this MCTP introduction? You enjoyed this?
It's very good. It was very nice.
Okay. So because I don't find a lot of people interested now on Monte Carlo, or the EGS part. Okay, I'm not getting, but I'm getting a lot of requests for
I installed it
making
in
cluster.
the Ubuntu machine, but I could not know how to proceed further to connect with the EGS.
Yeah,
That's all.
yeah. So try to look at what we have done, and I haven't done it actually on Ubuntu machine, MMCTP, but try it. Is a standalone machine or you have a virtual machine?
No, it's a standalone machine.
Okay. So try that. See if you have access to a DICOM file. Okay, a phantom. You can go to your planning system.
Phantom,
Just
yeah.
okay, generate. So scan if there is a phantom. Scan it. Import the DICOM file. There is something still I am struggling with also. That you could actually generate phantoms using this option, and I'm struggling with it. Today I was trying to fix that, but I did not have time to look into it. So in the RT patient import, you could actually hit on this physics button, and this should create a phantom for you.
Okay. It is
Okay,
a virtual phantom.
virtual. It's a phantom, right? So there it has a name. You can give it a name, image size, okay, and Hansfield units. So I tried to do this, and I want everything to be 0. Just put water. I want water phantom, and you create the patient. Okay. So then it should create it for you. But when I start to do the running of the simulations, there is I fail problem. So I'm trying to look into the code, what is happening. Okay. So the work that we have been doing, in Beam modeling and so on, it's not useless because this is, I'm using the Beam model that I have, tried to create in the past. I'm using it for NMCTP and so on. Okay. One thing, yes, there are, just give me a few minutes. Okay. Now I remember something very important. For NMCTP, we need to change the voxels for those XYZ. Okay. This is important. CD. Okay. There, if you go to your and I think it's in the instructions, it's written there. So we need to modify the macro, those XYZ NRC user macro. Let me put Emacs. Okay. So if I go down, okay, this here, the Imax, Jmax, and Kmax, by default, your dose, when you install EGS, this is going to be 128, 128, 128. These are the maximum number of voxels you can have in the dose XYZ. But we know for CT, at least in the X and Y, we have 512 by 512 voxels. In the Z, that's the number of slices. That could be 170. There will be a limit of the. So this is where you need to come here and replace the 128 with 512. And here for the Kmax, also for 512. So the upper one and the lower one. The one in the middle, I think 200 is going to crash. It's not going to compile. So 170, I find, it compiles. So once you modify this, then you need to, you type make clean. So you remove the compiled those XYZ, and then you make again, you recompile it. That is very important. Otherwise, the CTs, you get 512 voxels, and then it will give you segmentation fault, I think. Okay. Okay, then in that case, we'll conclude our session for today at this point. if you want to explore this more, please leave comments, in the classroom. Let me know what should we cover. I will try to update you with what I've been doing. And I hope that probably by next week, I will not get my other 8 Raspberry Pis. It's going to take maybe 2 weeks or more. But then I will have really a powerful cluster, here at home. Okay.
Thank you very much, Dr. Omid, and thank you everyone for joining us today. Inshallah, we'll meet next week.
Inshallah. Okay. Good night, everyone.
السلام عليكم.
Awesome.